Hello everyone, welcome back to the latest lecture session. We have been discussing aspects related to activated sludge process, where we were looking at removal of the soluble and biodegradable COD, right, or soluble organic matter which is biodegradable. In that context, I believe in the last couple of sessions we looked at design and then looked at a variation of the activated sludge process, which is now being widely adapted in India, which was or is the sequential batch reactor. In sequence, you have batch reactors being used more or less, it's in, not more or less, it's in the same tank though, right? So, first filling in and then aeration, and then you stop the aeration, let the microorganisms settle down, and then you have decantation, settling, and then you have the decantation, right? So, again we discussed that. So, today we will look at, I guess, a very minor design problem, just so that we understand the variables that we have looked at over the few or past few sessions, and then we will move on to looking at nitrogen and phosphorus removal. So, let us move on and see where we are. So, terms, I believe we looked at this, and I believe we would also have added some more terms. So, Q will give me an idea about how much or the rate at which the water is flowing into the tank, volume per time, right. So, volume per time, Q, flow rate. X, obviously as mentioned here, it will give me an idea about the microorganism concentration in the relevant tank. So, MLSS, MLVSS, that is how we typically measure that, let us say, right. So, volume of the aeration tank, typically we are looking at design of the aeration tank, because that is where we are assuming with good reason that the relevant reactions happen, meaning the oxidation of the organics. So, growth rate constant, for example, when calculating or trying to calculate various variables and also trying to understand how fast the microbes grow, you need a rate constant which might be, similar. To draw an analogy, let us say we have A goes to products, let us say, and K is the rate constant. Rate of this chemical reaction is K times concentration of A. So, here let us say I am concerned about how microbes are growing. Rate of growth of microbes will be depend upon mu times the concentration of the microbes. So, mu is equal to mu max into S by Ks plus S. S is the substrate or R waste, which is the food for the microbes, and Ks is the half velocity constant, where and it is equal to the soluble BOD5 concentration at 1/2 the maximum growth rate, right. For example, if this is the relevant graph, so this will be mu max, and at mu max by 2, this is Ks, that is what it means, right, and rate of growth of microbes that we just looked at. Specific yield or yield, we know that the microbes are going to grow, right, or cell synthesis is going to take place based upon the transformation of the organics, right. Not all the organics are going to be oxidized, considerable fraction of the organics are going to be used by the microbes for production of new cells. So, how much new cells will be produced or mass of the cells produced per mass of the substrate that is being consumed. So, that is going to be equal to 1, obviously, not 1, pardon me, less than 1, obviously, and the readily biodegradable and soluble COD, which is R waste, which we are trying to remove. This is what we are trying to remove or degrade in our particular system. That is the whole point of the design, right. And again, I guess X we did look at it. So, Ks we just looked at it. Kd, for example, we know that the rate of growth of microbes, we just looked at that. So, rate of decay, either due to death or due to predation or such, you are going to have decay. So, again that is going to be depend upon its own rate constant Kd, decay rate for microorganisms, into X, let us say, right, Kd into X. Qw, I guess to be wasted, flow rate of the liquid containing the microorganisms to be wasted. We looked at this as in from the secondary settling tank, after the microbes settle down, the sludge, most of it will be recycled typically, and some of it will have to be wasted otherwise, right. And that will the flow rate of this Q, flow rate of this wasted sludge is Qw. Xe is the concentration of the microbes in the effluent, which is typically less, that is what we want. Xr is the concentration of the microbes in the recycle or in the wasted sludge, let us see, right. So, that is something to keep in mind. So, let us try to look at a question and understand the different variables. A town, this is from I believe Mackenzie or Davis. A town has been directed to upgrade its primary wastewater treatment plant. So, earlier it was only primary, meaning they were looking at mostly suspended solids, right, grit removal and so on and so forth, and then suspended solids removal, and along with suspended solids some BOD, around 30% BOD would have been removed, and now they want to build a secondary plant. Secondary plant, we are trying to remove most of the soluble what is it, COD or the soluble organics, let us see, right, that can meet an effluent standard of 30 milligram per liter of BOD5, okay, and 30 milligram per liter of total suspended solids. So, the way I wanted the TA to do this, I did not want to look at this. Hopefully, that was taken into account. So, I see this. So, assume that for this particular part, the effluent concentration of BOD5 that is required is not 30 or such, but that it is 10 milligram per liter. That is the one that is relevant in the Indian context in the recent years, since the recent or couple of years, and this is in 2020, this year is 2020. So, I wanted to use 10 milligram per liters as the effluent BOD concentration, let us see. So, that is what I want, S effluent or S has to be 10 milligram per liter, and completely mixed activated sludge system, fine. What are we requiring or what do we need? Obviously, I need to know the volume of the aeration tank, and for that I have some data. So, primary from the primary plant, this is the flow rate. So, this is my Q, and this is the BOD coming into the secondary tank. So, this is my S naught or the one that is present initially. Assume the following values for the growth characteristics. So, I know this half velocity constant Ks is there, and mu max, okay, we already looked at it. So, maximum growth rate constant, that is also there, 2.5 days, right. So, how do we get this? Typically from what do we say, laboratory tests. K decay is there, the yield coefficient is there, milligrams of volatile suspended solids, which give us an idea about the microbes per milligram of BOD5 which is consumed, that is the yield, let us say. So, mass of the microorganisms being produced per mass of the organic matter being consumed by the microbes. Assume that the secondary clarifier can produce an effluent with, okay, this we will not look at or consider for now, and that the MLVSS, right, mixed liquor volatile suspended solids is 2000 milligram per liter. So, let us look at the relevant approach. So, at the end of the day, I need to be able to calculate volume. Volume is theta times Q, let us say, right. So, I believe in that question I should have also asked to calculate theta C. So, obviously, in this question I want to calculate theta C and volume. Volume, for that I need theta hydraulic retention time. This gives me an idea about how much time the water molecule is spending in the system. This will give me an idea about, or this is the cell residence time or solids retention time, SRT, and this is the HRT. Note the difference please. This will give me an idea about how much time the microbes are spending in the system. Volume of the tank will be the hydraulic retention time theta into Q, let us see. So, for that theta I need to calculate that, right. So, again we can calculate that. So, to be able to calculate theta, I guess we have this particular equation derived from the mass balance. If you remember, we looked at three major equations. One was based on the mass balance on the microbes around the total system, right, around the total system. These were the aspects that were considered, and then for the same system we also looked at mass balance on the substrate, yes, and then I believe we looked at rate of growth or R net of the microbes is equal to rate of growth minus rate of decay, R net, right. And we can also understand the rate of substrate utilization in terms of Y and rate of growth of the microbes, let us see, right. So, these were the, so 1, 2 and 3, these were the equations we played around with. we know that rate of growth is equal to mu times x, and we play around with them and we got these particular equations. So, how do I get theta from this equation? I can get theta. As we know, x is dependent upon both theta and theta c. So, in this equation I have all the other variables if you see, but I do not have theta c. So, again I need to calculate theta c. So, for that I have another equation that is out here. So, I guess we can look at that. So, as we know, substrate in the effluent is a function of theta c, and we already have this as I said, for discharge into Ganga, we know in India it is 10 milligram per liter, that is why I am using this, and this equation is a function of theta c. And if you see Ks, we have that Kd, this is not a capital K, this is small kd, right. Theta c we are going to calculate, theta c we are going to calculate, mu max we have that, again Kd, decay constant we have that, and S is 10 milligram per liter. So, from this I can calculate theta c, and I know that x, there is an equation where x is a function of theta and theta c. So, since I already have theta c and I have x and theta c, so I can calculate theta. Let us say x is there, MLVSS or MLSS. So, yield is given, Kd is given, theta c we just calculated. S naught is what, 84 milligrams per liter, what is coming into the system, that is 84. This is with respect to substrate, I guess, S naught, S effluent 10 milligram per liter, right. We have this, theta c we calculated above. So, from this equation I can calculate theta. Once I calculate theta, I can substitute here and get the volume of my tank. So, that is the approach. So, in general, if other variables are given, you will play around with it. But sometimes depending upon the level of difficulty, at least from a theoretical point of view, we can change the assumptions, right, and assume different or give you different conditions. So, that is the reason why we looked at the mass balance. In general, if I just give the equations, you will not be able to deal with either the theoretical questions or understand how the system, what do we say, depends on different variables or is interlinked between different variables, right, and the practical scenario too. So, from both the aspects we needed to look at mass balance. So, that is the reason we looked at it. So, let us move on. So, what do we have? As I mentioned in this question, I wanted S effluent or S to be 10 milligram per liter. This is the acceptable BOD5 in the effluent, let us say. So, theta c, as I mentioned, we can get this from this equation, right. So, this is S, I guess, and what are the different variables, Ks and so on and so forth, and from that we get a cell residence time, as in the microbes are staying in the system for a time of 5.6 days. As you see, it is considerable time. From that we are substituting into the equation for x, which is a function of theta and theta c, to calculate theta, and x is nothing but, and that MLVSS, right, is 2000 milligram per liter, that is equal to x, that is what we are assuming to be x, right. And okay, so from here we calculated theta. So, one aspect to note is this is, I guess, an R or less than an R, is it? Okay, it is less than an R, but it will typically not be so low, right, but it is not unreasonable either. So, you see it is just more than, I guess, or about half an hour, but you can look at how much time the microbes are spending in the system, consider and compare that with the time that the water molecule or the organics are spending in the system. Why is this feasible? Because in our system, which is like this, right, if this was the case, both theta c and theta would have been equal, but because we want lesser volumes, right, and good level of removal while ensuring that the volume of the tank is less, what are we doing? We are capturing the sludge or the microbes and then we are putting that back in. Because of this recycle, theta c is far greater than theta. So, that is what you see out here. And then volume of the aeration tank, obviously theta is equal to V by Q, and we now can get the relevant volume, which is 228 meter cube, right. So, that is good enough there. So, let us move on to the next major aspect. Until now, what have we removed, right? Let's just take a quick recap. So, preliminary treatment, first we want to lift the water from one head to the other. Okay, so that's one thing. And what else do I want to remove? I want to remove particles that can mess up my machinery and such, right? I'll have different types of screens and such, yes. And then I will remove the heavier particles, grit, which is relatively inert, right? And this is during or headworks or preliminary treatment. And then in primary, I will, again, this is optional when wastewater treatment plant, depends upon your own what do we say, priorities, because here if you remove it, you will have a lot of sludge which you need to deal with. So, that is up to the relevant plant designer or such. Primary treatment, what am I trying to remove here? Primarily those compounds that are suspended in the water or wastewater, but which are heavier enough to be removed reasonably or within a reasonable amount of time. So, mostly suspended matter and some BOD also, I think we mentioned around 30%. And then in the secondary treatment system, what are we trying? We are trying to remove all the other BOD and any or some of the suspended solids. That is what we looked at until now. But with increasing urbanization and then greater pressure on the water resources, and the water system is not able to recoup itself, what do we need to look at? We also need to look at removal of these nitrogen and phosphorus nutrients, right? We looked at, I think, examples, some what do we say, eye-catching examples from China and such, right? So, we will look at how to remove these nutrients which are nitrogen and phosphorus. So, nitrogen removal, we will look at the processes and what are the requirements, and then obviously from the requirements we can look at the design configuration, right. Again, this is relatively straightforward, as in the removal of organic matter or BOD, what is the principle? The microbes need energy, right, and also they want to synthesize new cells. So, they are going to degrade these organic matter by using an electron acceptor. What is the electron acceptor? That is the oxygen you are pumping out. So, the principle is more or less the same in nitrogen removal. So, that is easy. In phosphate removal, it is a bit more tricky. So, we will look at that. So, there is a particular removal mechanism, we will understand the mechanism, and we will see why we need to have both anaerobic and then aerobic or alternating conditions of anaerobic and aerobic. We will look at why, yes. And okay, in that context we will look at the requirement for the sequential conditions, maybe look at a couple of configurations, as in if you want to achieve what do we say, phosphorus removal, how do you need to look at the plant or redesign the plant, let us say. We will just look at that briefly, and if I am not able to achieve that, I can remove phosphorus by chemical precipitation. So, we will briefly look at that aspect. I believe in this session we will be mostly looking at this aspect, and in the next session we will be covering phosphorus removal. Let us move on. So, first, nitrogen removal. What are the forms of nitrogen? We already discussed this in, I believe, one of the earlier sessions, but a quick recap. So, we have organically bound nitrogen, nitrogen that is bound to organic compounds, NH3 and NH4 plus, right, and NH4 plus and NH3, they are in equilibrium typically based on the H plus or pH of the solution, and you will have a equilibrium dissociation constant. Again, that is acid base environmental chemistry, you can look that up. And then depending on the level of oxidation, you can have nitrite NO2 minus or nitrate NO3 minus. So, these are the forms we are concerned with. Typically, we measure them as TKN, okay, nitrogen. So, that will give me an idea about both the organic nitrogen, organically bound nitrogen, and ammonia. Why am I concerned typically about this? Because this is the nitrogen content that can consume oxygen. That is why I am concerned about TKN. And in general, organic nitrogen is relatively easily degradable into ammonia, let us see, okay. And total nitrogen, obviously, as the name indicates, it is TKN plus the oxidized forms of nitrogen, which are NO2 minus and NO3 minus, right. As you can see, this is a reduced form NH4 plus or NH3, and NO2 and NO3 3 minus, as you can see oxygen here, relatively more oxidized form, right, reduced forms of nitrogen, and after being oxidized in the presence of oxygen by different microbes, they will be transformed into or oxidized into nitrates and nitrites, right. So, let us move on. So, nutrient from the CPHEO manual, and if you are discharging, what do we say, water or treated wastewater into inland surface water, let us say. So, I believe people have been revising it. So, ammoniacal nitrogen, right, as N, expressed as N, this is not NH4 plus itself, but as N, and then TKN again expressed in the units as N. So, you have the different standards again for free ammonia, let us say, right. Okay, but typically I guess we have decreased these values, and dissolved phosphates value is much lower. Again, why is that? Because typically in surface waters this is the limiting nutrient. Let us move on. And again, why am I concerned with removing nitrogen and phosphorus? So, we looked at algal bloom, as in when you have the essential nutrients which are nitrogen and phosphorus, you can have what do we say, explosive growth of algae, and later when the algae die, they are a source of organic content for the microbes. Microbes consume the algae in the presence of oxygen, or what do we say, by consuming oxygen, and thus you are going to have depletion of oxygen and relevant septic conditions. Other than that, this algal bloom will also interfere with the aquatic life beneath it, the penetration of light will be affected. So, you are going to have considerable issues. Some kinds of algae are toxic to us, yes, and what else, I guess. Okay, those are the major aspects. I would have covered most of the aspects earlier too. And okay, so nitrogen, with respect to nitrogen, NO3 minus is not, what do we say, something that we would want to prefer to be in our drinking water. It is a regulated compound, NO3 minus. So, that is one more reason to remove these nutrients, let us say. For example, we talked about algae and eutrophication, and in that context we talked about algae. So, typical what do we say, formula, let us say, to represent algae is C, H, O and P, and these are the ratios of the relevant what do we say, elements here, right. And as you see, the ratio of carbon, nitrogen, phosphorus is 106 to 16 is to 1, molar ratio obviously, right, 106, 16 is to 1. So, this is also the Redfield ratio, if you see that. This will give me an idea about, let us say, which one is the limiting nutrient, or if I know the ratio right now, let us say of a particular lake, and I see carbon, nitrogen and phosphorus, and I can calculate and see which one is the one that is the missing link. So, typically a lot of carbon will be present. So, carbon is not the limiting factor. Usually we are dealing with lack of nitrogen or phosphorus, but in inland surface water bodies, typically phosphorus is the limiting nutrient. So, you can look at this ratio of nitrogen phosphorus or carbon to nitrogen phosphorus and understand which is the limiting nutrient. Let us move on. So, here is a good schematic which gives us a holistic view. So, I have organic nitrogen, right, and where is it coming from? From proteins, and in our urine you have considerable urea, right. So, again we take in proteins, yes, we synthesize them, some of it or some forms of nitrogen are going to be released, again amino acids and such. So, bacterial decomposition and hydrolysis, let us say, you are going to form ammonia nitrogen, right. So, organically bound nitrogen will be transformed into ammonia nitrogen, and this is relatively fast, okay. And some of this ammonia or the nitrogen will be used by the bacteria. I think we saw that it was around 12% of the nitrogen content. This we looked at when we were looking at the oxygen requirements, right. And we saw that, or we deducted this amount, let us say. And again there is going to be a cycle, because you are going to have lysis, right, or death of the relevant microbes and such. So, more or less you have ammonia nitrogen that is in equilibrium with the organic nitrogen, but the one within the cells itself. So, depending on the kind of bacteria and the concentration of bacteria, so you are going to have a balance between ammonia nitrogen available for oxidation and the nitrogen in the bacterial cells. Okay, so, I have NH4 plus, right, and as you can see, this is a reduced compound, right, and in the presence of oxygen it can be oxidized by microbes, right, to this is nitrite and this is nitrate, okay, NO2 minus and NO3 minus. So, it will be oxidized to NO2 minus first and then to NO3 minus. So, here we are forming the nitrates, nitrite and nitrate. So, that is why this process, entire process is called nitrification, yes, nitrification. But I am still ending up with nitrogen in the water. These are remarkably soluble. I can't remove them by precipitation or by trying to change the phase from wastewater to the gaseous phase. I can't do that, right. So, what do I need to do? I need to transform it into a phase which will allow me to remove nitrogen from the water. So, that phase is not the solid which we would have tried to achieve by precipitation, but by changing it from the aqueous phase, meaning dissolved in the water, to the gaseous phase, right. So, here the nitrate will be what do we say, will undergo denitrification into nitrogen gas. Here again, as you see, it is NH4 plus is the reduced compound electron donor, electron acceptor is oxygen, and then you have formation of NO2 minus or later NO3 minus. So, here there is no role of organic compounds. So, thus they are called, I mean, the kind of microbes are autotrophs. But here let us say what is happening here. You know, you have NO3 minus and you want that to go to N2, right, oxidation state is 0. Here it is, what is it, minus 6 from here, x plus minus 6. So, it is plus 5, let us see, right, from plus 5 it is being reduced to 0, the nitrogen oxidation state, let us see, right. So, 3 into minus 2 is minus 6, x minus 6, the total oxidation state is minus 1. So, oxidation state of nitrogen in NO3 minus is plus 5. So, here it is going to N2 or being reduced to N2. So, it is being reduced, right. So, it needs a source of electrons or an electron donor is required. So, what is the electron donor? It has to be carbon from the wastewater or any source of organic form of carbon which is relatively reduced. So, this is the electron donor and this is the electron acceptor, right. So, one thing to note is that in the usual activated sludge process where we are degrading the microbes, not microbes, the organic content or our waste, oxygen is also the electron acceptor. So, that is good enough for nitrification. But for denitrification, as you see, NO3 minus is the electron acceptor. So, if oxygen is present in the system, denitrification will obviously not take place, right. If you look at the thermodynamics, microbes that use oxygen as the electron acceptor in the presence of organic content typically gain more energy. So, those kinds of microbes will be prevalent, especially if you have oxygen, right. So, that is the reason why I guess you have to prevent oxygen from being present when you undergo or try to have denitrification, right. So, what else? I guess that is it in a nutshell. Let us see what we have. Okay. So, the kinds of bacteria that we have, for example, we know that NH4 plus oxygen goes to nitrite and nitrate. So, here there is no organic compound, no C, H, N, O, X, Y, Z and A. Okay, these are the stoichiometric coefficients here, let us see. So, NH4 plus oxygen. So, there is no need for an organic compound here. So, these are heterotrophs. I seem to have put in a typo here because here you do not have the need for any organic source of carbon, right. These are autotrophs, not heterotrophs, right, but they are aerobic because you have they need oxygen, right. So, chemotrophs, yes, because they derive their energy from chemical sources, but heterotrophs are when you have what do we say, organic compound as the source of energy, let us see, but here it is not organic carbon. So, these are aerobic autotrophs, let us see, autotrophs. So, what do? They either, we have two kinds, ammonia oxidizing bacteria or nitrate oxidizing, let us see, right, nitrite. So, ammonia oxidizing bacteria take it to NO2 minus, and another kind of bacteria nitrite oxidizing, they take it to NO3 minus, right. So, these they take oxygen, ammonia, right, nitrifiers, and finally, the end product is nitrate. So, I am left with nitrate. So, NH4 plus is taken and oxygen is taken, and these aerobic autotrophs degraded to or oxidized to NO3 minus. And NO3 minus, we now have anoxic conditions. Anoxic as in there is the electron acceptor is not oxygen, but the electron acceptor is nitrate, right. So, these are anoxic, yes, because no oxygen, but these are heterotrophs as in this is the electron acceptor, but there has to be an electron donor. Electron donor has to be an organic compound. Because it is an organic compound, it is an heterotroph, and because it does not use oxygen, they are anoxic, let us say, right. So, these are called the denitrifiers, yes. So, that is what we have, organic compound and anoxic heterotrophs, they degraded to nitrogen gas, and nitrogen gas will leave the system, and that is how, as you see, your nitrogen is being removed from the system. First to NO3 minus and then reduce it to nitrogen gas, and then it is leaving the system, right. So, I believe I am almost out of time. So, let us just quickly summarize this slide and we will end for today. So, biological process, I think we discussed this earlier or right now too. Ammonia oxidizing bacteria, ammonia is being oxidized to nitrate, and then this nitrite is being further oxidized to nitrate, thus we have nitrite oxidizing bacteria. So, overall though it looks like ammonia is going to nitrate, let us see, right. And some of these are autotrophic as I just discussed. CO2 goes to, what do we say, provide cell mass, it is not from, so it is inorganic source, it is not an organic source of carbon. So, that should be enough for this session. In the next session, I will continue talking about nitrification, denitrification. We will look at the mechanisms, and then we will move on to looking at phosphorus removal. Thank you.